Now let's have a look at, what happens if we have a fractional indice? And the only one we really worry about is the square root, so power of a half. So we look at this one, y equals the square root of the function. Right, well, we know for a start we can only find the square root of a positive number. So anywhere where the original graph was negative, it's just going to disappear. You can't find the square root of the negative number. So here's my original graph, and we'll say goodbye to that bit, and goodbye to that bit. It's like it's not even there. Okay? All right. So the next bit, because we're finding the positive square root, we know that the answer is always going to be positive. So that'll be true. Now, that'll be opposite to the last one. If you find the square root of a number bigger than 1, then it gets smaller. So this time it'll be below the original graph. But if you find the square root of a number less than 1, that will get bigger. And so it will go above. So opposite to what happens with the powers. Square root of 1 is, of course, 1. So we can plot those points in. And we'll know that above the 1, well, that's now going to get smaller, so it'll be below the curve. Below the 1, it'll be above the curve. Square root of my horizontal asymptote, well, that's a number smaller than 1, so it'll get bigger. Can't pass 1, of course. It's still going to be less than 1. Vertical asymptote, that's not going to change. But now here's an interesting thing. Let's have a look at the derivative. If you differentiate the square root of function x, so function x to the power of a half, you'll get, well, it's actually on 2 root fx, but the 2 is irrelevant. That's a little misprint there. But what I'm more interested in is the derivative of the function. Okay? So the original graph had stationary points. So the original graph, where there is a stationary point, my new graph will still be a stationary point because that derivative will be 0 as well. But have a look at what happens with x-intercepts. The original graph, function x was equal to 0, now means we have 0 on the bottom of the fraction. Undefined. It's not that the function's undefined. Function exists there, but its derivative is undefined. Okay? So we're going to have critical points there. It might be a vertical tangent. Something like that. It might end up being a sharp point, like an absolute value graph. More likely going to be a vertical tangent, to be honest, but we'll see some examples. How to work it out. Here's a little, table, which I pinched out of a book. I'd like to take credit for it, but I can't. If you know what the original graph is, that can help you out. Because remember, you're finding the square root of the original graph. So say the original graph was x to the power of 4, then you know the square root of x to the power of 4 is x squared. So actually, that critical point turns out to be a stationary point. Yeah? Remember, stationary points are critical points. We more normally associate critical points with vertical tangents, but it could be stationary points. So in that case, if we had x to the power of 4, it would be the square root of function x there would be a turning point. X cubed, well, we don't get a vertical tangent on that one. It just stops, bang, at a sharp point. So you can't really draw the derivative there because it stops. So we just get a missing point. Whereas x squared, we get something like an absolute value graph. Why? Because the square root of x squared is x, the straight line. So it's like you're getting 2 straight lines, 2 y equals x's coming in together. 5 on 3 square, you end up with a vertical tangent there. And you can also see 4 on 3 as an example. You also get a vertical tangent, but it exists either side on that one. So you can get some really interesting shapes if you know what the original graph looks like. Now, of course, I don't know the equation of this graph, so I can only guess, what they are. As long as I justify myself, we'll be okay. So, all right, my stationary point will become smaller, because it's bigger than 1. At each of those x-intercepts, we're going to have critical points. Now, here we go. Oh, that was really hard to do. I think I really exaggerated my vertical tangent over here. But what was my logic behind why I did it that way? Well, whilst I don't know the equation of this blue curve, the x-intercept looks like a straight line, I suppose. That's more important. Look at that. If I find the square root of y equals x, I get the square root of x. If you were to draw the curve y equals the square root of x, it's a parabola on its side. So you're going to get that vertical tangent there. It's going to come in vertical. And that's what I've tried to do here on each of those points, create the vertical tangent. Over there, well, this looked like, I guess, coming through like a parabola on its side. So it would have been the square root of the square root, which would be the fourth root. Well, again, an even root would be a U shape on its side. So I'd get that vertical tangent. So I'm picking vertical tangents for those. But also notice how it goes above the curve, below the curve, above the curve, things like that. Ah, there it is in all its glory. Okay. So square root of function x takes a little bit of thinking about those x-intercepts. What exactly is going to happen? Now, another question they like to ask, instead of saying y equals the square root of function x, they ask y squared equals function x, which is slightly different. Because if it's y squared equals function x, you now have y equals plus or minus the square root of function x. So what happens? It just reflects in the x-axis. Because you've got both the positive square root and the negative square root. Just like our circle, if you like, is built up of the positive square root for the semicircle, the negative square root of the semicircle. Same idea. Okay, so we'll add those in as well.